G'day everyone. In this lecture, we're going to look at two-level system with a time-dependent perturbation V as a function of time. It's going to be a very mathematical kind of lecture and a lot of maths. So you might want to slow down and do it yourself, following the notes, and you might want to skip ahead for the boring bits. So we start off with a two-level system and some arbitrary Hamiltonian H naught psi A equals EA psi A, and H naught psi B is equal to EB psi B. So we've got two different levels, EA and EB, with corresponding wave functions. And we only have these two levels. But what we'll see later on is that often you can just ignore any other levels anyway in useful cases. So if we've just got these two levels, then we can write for any wave function at all, and here the CA and the CB are a little bit different to what we had in the previous video. Here I've separated out an additional factor of e to the minus IEAT over h bar. There's still some time dependence in the coefficients CA and CB, but if the Hamiltonian doesn't depend on time, then the CA and the CB are constants. In other words, in that case, all time evolution would be carried by the factors e to the minus IET over h bar. So now we posit that there is a time-dependent perturbation, V of t, and that is what's going to drive the time dependence of CA and CB. So now we go to our time-dependent Schrödinger equation, which is H psi, which is equal to, now it's H naught, which is the time-independent Schrödinger, time-independent Hamiltonian, some time-dependent perturbation, and that is I at h bar d psi by dt as usual. So now we're going to substitute in our psi of t. On the left-hand side, we'll have CA, and remember this is a time-dependent CA now. I'm just not going to write the function of t all the time because then it'll just take too long. I'm able to take the CA and CB, which are not functions, they're just numbers. They're time dependent, but they're just numbers. So H naught and V will commute with those numbers. And on the right-hand side, all of the time dependence is carried in the CA and the exponential factors, which we've separated out. And so now we have to put in two terms rather than just one, but it's worth it for us. So that's the first term and on the right hand side, and the second term on the right hand side is the same thing but for CB and psi B. Okay, so we've expanded that out, and now what we're going to do is cancel the static terms. And the static terms are the ones for H naught. So you can see, for example, here that if I took H naught and I act on psi A, then I pull out an EA psi A. Sorry, EA psi A. And so this term and this term are going to cancel each other. And similar for psi B. So cancelling the static terms, I will get so that's not too complicated an equation. And now what we're going to do is our old trick. You multiply by the bra and integrate. And so that gives us CA psi A, and I'm just going to write the V psi A as a ket with my phase factor still intact. Unfortunately, these phase factors matter. And on the right-hand side, I've got IH bar. The first term there is going to be non-zero because it's psi A. So that's 1, e to the minus IEAT over H bar. But the second term will be psi, it'll be like psi A, psi B, and so that one's going to be 0. So we can leave that one out. Now it's a good time to define similar to when we did perturbation theory, we define a VAB, the matrix element, but now it's a time-dependent matrix element. It's psi A, V of t, psi B. Time-dependent perturbation, time-dependent matrix element. And therefore, we can write CA dot is equal to minus I over H bar. So that's the right-hand side now. And that's equal to minus I over H bar CA VAA from the left-hand side of the previous equation plus CB VAB. And now there's a phase factor that we have to take into account. E to the minus I EB minus EA. Oops. T over H bar. And similarly, if we multiply the equation by psi B instead and then integrate, then we'll get an equation for CB dot, which is very similar, minus I over H bar, CB VBB plus CA VBA, and a phase factor like this. And usually we will define H bar omega naught as being the difference in the two energies, EB minus EA. So those phase factors will be e to the minus I omega naught over, e to the minus I omega naught T and e to the plus I omega naught T for those two equations respectively, where EB minus EA is greater than 0. So in these equations, if we look at these two equations, we're basically done. We've got two coupled ordinary differential equations. CA VAA is a function of t. VAB is a function of t, and so on. And so in principle, now we can solve these. We've got initial condition for CA and CB, and we just evolve this thing in time simultaneously. So these are two coupled ODEs, and so we can only solve these exactly in special cases. Now, one of the extremely important special cases that we can solve exactly for is as follows. So the example we've got is we want to solve for a perturbation which has the following properties. VAA and VBB are both equal to 0. This is not an unusual case, by the way. And VBA is equal to some number UBA over 2 e to the minus I omega t, and VAB is equal to UAB over 2 e to the minus I omega t, which is the complex conjugate, VBA. So this, and we'll have some initial conditions as well. So we'll put with CA at time t equals 0 is 1. In other words, it's in the ground state because EB is greater than EA. So this is a typical kind of situation. This is, for example, the potential that you would get from a laser with a monochromatic frequency omega. And so it's an oscillating electric field, which would have an interaction with a two-level atom, for example, a two-level atom or quantum dot or something like that, or a qubit. UBA will then be the interaction of that qubit or that atom with light. And so that electric field will be oscillating. That's this part. And the electric field oscillating has this interaction with the qubit. And so because it's an electric field, as we learnt from the ordinary perturbation theory, the VAA and the VBB will be 0 at first order in perturbation theory. So it's kind of a normal situation to actually happen. So this one looks odd, but it's actually very, very important in reality. In this particular case, we will have the equations simplified down to this. CB equals minus I over H bar, VBA e to the I omega naught t times CA, and CA dot is equal to minus I over H bar, VAB e to the minus I omega naught t, CB. Remember, omega naught is EB minus EA and is greater than 0. To solve these two coupled ODEs, we can turn it into a second order ODE. And so we want to turn that into a second order ODE in one variable. We could do that, for example, by writing CB double dot equals So in this way, I've converted it from two first order ordinary differential equations to one second order ordinary differential equation in CB. And so I can solve this by just writing it out as a kind of quadratic form and then solving it in the ordinary way, in the usual way. We can solve this easily by using a trial solution. Where A and R are just constants. To make our lives a little bit easier, I'm going to define this omega r, which is just the square rooty part. When you're solving this at home and checking my work, just make sure that you keep track of all of the i's, because they're all important, imaginary parts. And so with that definition, we have r is equal to I omega naught minus omega over 2 plus or minus I omega r. And so putting that back into our equation for CB, our trial wave function, we get A So that's the most general form of our trial solution that fits the second order ODE. And now we need to put in the boundary conditions. So that's a solution for the time being of CB as a function of time. Okay, let's go back to CA. So that gets a little bit messy, but it's not too bad. Continuing. Okay, so we've got some kind of complicated function of omega, omega naught, and omega r. Let's just clarify for a second, just remind ourselves what those are. Omega is the driving frequency. Omega naught is the energy difference between the two levels. Now we put in our boundary condition. Cool. And that is my expression for CA as a function of time. And that one looks pretty complicated, but it's not so bad. And especially because CB of t now looks pretty easy. CB of t becomes which has a particularly simple form. And maybe a bit of homework while we're here. Check that the squares of CA and CB are sum up to 1. In other words, that the state is correctly normalized. So this is basically saying, right, okay, so we've got this probability of being in the state A, and that's CA squared, and probability of being in the state B is CB squared, and so those probabilities should sum up to 1, because it's either in the state A or the state B for a two-level system. So that was a rather complicated derivation. You should practice it at home, maybe just once. And now I want to talk a little bit about what it means. So basically you hit this system with your laser, and it's in the ground state, and you wait some time t, and then you measure, is this in state B or is it still in the ground state A? And so that is the probability of going from A to B at time t, and that's equal to CB of t squared, which is equal to this UBA over 2h bar omega r squared sine omega r t squared. So there's two parts to this. Firstly, there's this intensity. That's the intensity if you like, I UBA over 2h bar omega r squared, which we could also write as UBA squared over 2, and if I just expand out the h bar omega r, that's omega minus omega naught squared plus I'm sorry, that should have been an h bar squared at the top. And so what does that look like? Right, UBA is just some constant. And what we've got here is a function of omega minus omega naught, which is a Lorentzian. So it looks very much like a kind of a driven oscillator type problem from classical physics. You've got a Lorentzian profile centered around omega naught, which is the natural frequency of the system. When omega equals omega naught, you have the maximum driving from A to B. If omega is far from omega naught, you're far from the natural frequency, then you have an inefficient drive from A to B. So this really does look like a classical kind of driven oscillator. And the other point is that you're going to have the oscillation part, sine squared omega RT. So if we look at, these are called Rabi oscillations. If we look at the probability of going from A to B as a function of time, it looks something like this, where the probability is proportional to sine squared omega RT. In other words, if I leave my laser on for the correct amount of time, I can maximize the transition probability. But if I keep the laser on longer, then the probability goes back down to 0. So with my laser, if I leave it on for a certain amount of time, I can get it up to here, then I can drive it back down again, then I can drive it back up again, and so on. And these are Rabi oscillations. And lastly, I would like to point out that the resonance condition for this driven oscillator looks something like this, right? That's just literally from this formula here. Yeah, and you can see that if omega is close to omega naught, then it's efficient. So this resonance condition means that we can use our two-level system even when there are more than two levels. So that was a rather long but important example of a two-level system being driven by a perturbation that varies in time. And it leads to some very important results for atom optics, which means that we can actually drive atomic transitions with lasers, and we can do so in a very coherent way. So that's what we're basically seeing in this result. Thanks very much, and I'll see you next time.